Hello, I'm Daniel and I want to show you a quick demo on Profiler. But before that, let me give you a little introduction. Okay, let's start with this. So knowledge is important for a lot of NLP tasks. So somehow we need to formalize knowledge and induce it into our problems. What we are doing here, we have a graphical formalization for knowledge, and the result is a tool or resource, we call it Profiler, which contains a lot of statistics for knowledge schemas. So, how do we represent the knowledge? Here we represent knowledge with a graph. So in a graph, we have a bunch of nodes and a bunch of edges which connect the nodes. For each of these nodes, we have attributes. The attribute can be part of a speech tag, word, part of a speech tag here in this example. And for each of these attributes, we can have some set of possible values. For example, if the attribute is part of a speech tag, the possible values can be noun, noun phrase, verb phrase, and so on. So in this example, the value for this attribute is noun. For here, again, the value is noun, and again, here the value is a word. The roles or relations are basically what creates connections between nodes. So these relations can be subjective, objective, or anything else that we define. The possible set of attributes and values that we use in the profiler are represented in these two tables. The attributes are words, can be word, the raw text, can be lemma, parts of speech tag, NER, and Wikifier label, and verb senses. By Wikifier, we mean the link of the entity to its Wikipedia page, which uniquely identifies it. And verb sense are based on a verb net. So basically, for each verb that you discover, it has its unique sense. So you might have grow with multiple senses. One might have planting, one might have the meaning planting, the other one might have the meaning of growing up. And these are the possible values for roles, before, after, and so on. I will show more example on these later on in the demo. Some terminology. Schema. Schema is a graph which we use for definition of the knowledge. For example, each of these graphs are schemas. What does this schema show? This basically says this defines the set of all verb phrases which happen after the word Obama. What does this show? This is the set of all pair of verb phrases which such that one happens after the Obama and the other one happens before Obama. For each of these schemas, we will have statistics inside the profiler. And something common between all of these, each of these knowledge schemas is their pivot node, which in this case is word Obama. When we combine all of these schemas with common pivot node, they create a profile which explains something about this pivot node. We have this ambiguation inside the profiler. What does that mean? So that means that if we have two sentences with the same Seattle string, they might refer to different things, as we have this in reality. So this Seattle in this sentence refers to the Seattle city, and in this sentence, Seattle refers to the Seattle Seahawks. And by this ambiguation, we mean that we make difference between this Seattle and this Seattle. And where does this ambiguation come from? We have tools which connect entities to their Wikipedia links, and by Wikipedia links, we can uniquely disambiguate an entity. How do we acquire this knowledge? So we get a bunch of Wikipedia pages. We annotate them with Illinois Cloud NLP tools. The resulting thing is around 1,500 gigabyte annotated documents. The resulting thing is processed with MapReduce in almost 3 hours and about $400. And the resulting thing is 200 gigabytes of annotated data, which in the form of profiles. Something which I implicitly mentioned, but I want to be explicit about. Pivot nodes here in our work are disambiguated, and we have two types of disambiguation. One is with Wikipedia links, which we apply for entities. The other one is via verb senses. So each verb will have its own sense. The size of Wikipedia profiles is 3.5 million and 300,000 verb sense profiles. So let me show you the demo. Alright, let's try the demo. So this is the main page of the demo. We have multiple tabs. Let's start with the first one, graph view. So in this page, we have a bunch of graphs. This one, this one, this one, and this one. Okay, and in each of these graphs, well, you have one red node, which represents the pivot node. If I open the pivot node, I will see I can either choose verb or wiki entity. If I choose verb, I need to here enter a verb, for example, go, and I need to enter a sense, for example, 0, 1. If I choose wiki entity, I need to enter a wiki name, a Wikipedia entity name, for example, Seattle. And its label can be the Wikipedia link to the Seattle that we have in mind. For example, if we have Seattle City in mind, we need to enter the link to the Seattle City. I have the link here ready, so I'm gonna just use this, and I'm gonna click on query. So what does this mean? NER before. The role by default is before, and the attribute here is by default NER. That's why here we say NER before. And what is this table? Attribute is basically the set of all NER labels. So these are the values of this attribute, which is NER. And these are their frequencies. They're sorted by their frequency. An organization is the most popular NER label happening before Seattle, the city. Let's try something else. Let's try, instead of NER, let's try entity. So what is this? These are the set of surface strings for entities, and with these links, and which happen before Seattle. This is probably noise. This is probably some mistake in the extraction. Seattle happening before Seattle. You can just ignore that. When we have unmapped, it means that this is recognized as entity, but it's not mapped to something else. But if you look at this carefully, you can see there are a lot of things which make sense and in practice can be very useful. For example, Washington, University of Washington. A lot of these are actually very relevant to Seattle. Like for example, you might have a lot of sentences which mention LA next to Seattle, or American next to Seattle, Portland Film Festival in Seattle, Chicago, San Francisco, Pacific. Let's try something else. Dependency, and let's try noun. What are these? These are all of the nouns which are connected with a dependency path of length less than 2 to the Seattle. So Washington Seahawks, Sounders, Times, Mariners, University, WA, City, Festival, Portland. Interesting, huh? Let's try all of the noun phrases which are contained in Seattle. Seattle Seahawks, the Seattle Times, the Seattle Mariners, the Seattle Sounders, the Seattle area, downtown Seattle, Seattle Sounders FC, Seattle City, and so on. Let's switch gears from noun to go to verb phrases. Let's say verb phrase, what do we want? Immediately, let's try immediately after. Seattle is, Seattle was, Seattle based, Seattle won, Seattle to work, Seattle to begin, to join, beginning. Some of them make sense, some of them don't. So yeah, remember that all of these statistics inside the profiler can be, some of them can be very noisy, some of them can be less noisy. The job of this visualization is basically get to more sense into the statistics and try to choose the ones which actually make sense for the tasks that we have in mind. So the goal is to gain intuition about the knowledge that we have here. Let's try. So instead, how about this? Immediately before. I think immediately before is gonna make more sense because like verb happens usually before the Seattle name. Attended something in Seattle. Departed Seattle. Someone departed from airport Seattle. Someone was at Seattle. Someone's joined Seattle. It can be a name of team. It can be a name of. This partly can be a result of noise. Someone arriving at Seattle, someone born in Seattle, someone visited Seattle, someone founded something in Seattle, someone represented Seattle. This makes, here in this case, before, verb phrase immediately before Seattle makes more sense than after. Let's try something else. Instead of Seattle city, I'm gonna try Seattle Seahawks. I have the link ready here. Okay, let's try something else. Let's try dependency. Let's try noun. Okay, so all of the nouns connected to Seattle with the dependency path. Seahawks, Cowboys, Bay, Washington, Saints, Patriots, Titans, Vikings, Giants. How about this? Let's change to noun phrase. Oh no, noun phrase. Yeah, noun phrase before. Yeah. College football, National Football League. A former professional American football player. Let's try entity. Entity before? Yeah. Football in football. Any of NFL, American football, college season, college football, draft. Apparently there's a lot of sport. Oh no, yeah, sorry. Yeah, it's already, yeah, it's about Seattle Seahawks, right? So we actually expected to see a lot of entities relevant to Seahawks here. So all of these are expected. How about this? We go to dependency NER. Okay, what are these? These are the set of all named entities, including their NER labels. Here the labels are included. In this table, the labels are excluded. So these are named entities with their surface string. So you can see Seattle, all of them are connected to Seattle. Seattle Seahawks, Houston Texans, Pittsburgh Steelers, and all of them are labeled as organizations. But so if you're using, you can one way of using this can be like filtering based on the label, like what type of entities with certain labels you want to use as features or any other way that you want to use it. Okay, let's switch gears and query from verb profiles. Let's go with verb attack and its first tense, which is the most popular one. And let's query this. Okay, what do we expect to see? NER before. Usually, the name entity happening before attack is a person. But after we expect that to be it can be a person, it can be a location, it can be organization or something else. So here the statistics are relatively closer to each other than in your before, which is mostly a person. There's a huge gap between this, the first one and the second one. Let's try NER connected with dependency. All of these are NERs which are connected with dependency. Um, well, to be more accurate, these are all of the named entities connected with dependency paths of length less than 2 to verb attack. These are their NER labels. This table, this basically is basically the same as this table, ignoring the table. So one might have more flexibility in this by using only rows with certain labels. Um, we can check noun phrases. For example, noun phrases. Let's say, yeah, let's try a different one this time. Let's say nearest noun phrase before. So these are all of the noun phrases happening before attack, and as you can see, so these are the things which commit the attack probably. If one person wants to use this kind of statistics, we can easily ignore these kind of pronouns, which have a very high frequency. These are really easy to filter out. What matters is the things happening after these. So in order to see what's going on more, I can just go to config and increase this size of queries to 100, and we will see this better. Okay, this is better now. So these are the things which attack. So the group, the convoy, the player attack, his men, the village, the Germans, the ship, the enemy, this squadron, the army, Nazi Germany, the French forces. So yeah, the point here was basically blindly using these statistics might be problematic. Instead, the right way is to gain intuition by visualizing the data and using them in the right way. If this changed before to after, nearest after, nearest after. So these are the things which are being attacked. Again, we have pronouns here. So midfielder, enemy, the fort, the castle, the player, enemies, pirates. Let's try this time entity. Oh, we don't have entity. Let's try something with dependency. Dependencies tend to be more clean. For example, dependency now. So forces attack, midfielder attack, army attack, enemy attack, ship attack, troops attack, aircraft attacked, dependency NER, Japanese attack. Oh, actually, I think we checked this. I don't know. So let's try. Instead of using this pairwise graph, let's try another graph. Just reload this to keep things clean. Let's try this. And 0, 1. Okay, this the flexibility of this graph in terms of the number of rows and attributes is relatively very small, much smaller than this, and this was more like experimental thing, so we just created to see what kind of things we can do this, and so we created these schemas only if they made sense to us, like in some ways. But so we didn't try many different settings only because like we didn't have a good reason to calculate them. So but it doesn't really mean that the statistics here is gonna make a lot of sense. So let's try this. So this is before, so this means that this is happening before this is happening after this, and here I'm just querying attack. So instead of okay, so I'm gonna set this to NER. Okay, So what is this? So this is the word happening. So this second is this attribute. This first one is this attribute, and these are their NER labels. Location is the NER label of this. Miscellaneous is the NER label of this, the first one. A lot of them might be noisy, but interestingly, the first one, which has a lot of high frequency in Wikipedia, Japanese attacked Pearl Harbor. This is interesting. This might be noise, these things. French attacked German. German attacked oil industry. Japan attacked Pearl Harbor. British attacked French. Or Soviet Union attacked Finland. Let's try this one. This is a little hard to explain. Okay, so this is this. So this is dependency. These two are connected via a dependency path of length less than 2. This is again dependency. These two are connected via a dependency path of length 2. These two, the attributes are aggregate. That means that we just ignore them. So we have them implicitly because of this relation here, but we won't see them in the table. What is this relation? This is choreographer. So, and this is the surface string, and this is the pivot for which we will have this surface string by default. So in the tables we expect to see this and this. These two are aggregated, and we expect to see the set of these words which are which are connected to each other via two other words which are co-referred to each other. So this is dependency, just to remind you. This is dependency, this is dependency, this is co-reference. So so the dependent of these two are expected to be linked via co-reference paths. Okay, now let's try querying from this graph. It's 6 elements. This is probably a little hard to explain, but let me try my best. So this is the pivot node, and we have 6 elements, and this is a verb, and here the pivot element is also a verb, so we're going to be able to only query from verb. We cannot really query from entities, so I'm just going to choose a verb, and let's choose attack, just like before. And let me increase the size of elements in our query to 100, and I query again. Good. This can be subject or object of its predicate. Again, this is subject or object, this element. The same thing holds for this. So this is, it can be either subject or object of this, subject or object of this. And the connection between these two is with coreference. So, oh, no, sorry. This can be before, this can be before this can be after this, or this can be co-referred before and co-referred after. Okay, now for the sake of experiments, let's try co-referred after. And note that we have object and subject here. What does it mean? It means that the two elements which are co-referred, this element has the role object, and this element has the subject. In other words, this is subject, since this is object. Okay, so here we have 6 elements, and here we have 6 columns. Okay, so this is basically our pivot. So let's see. Okay. So this basically this corresponds to this. This corresponds to this. This corresponds to this. And this corresponds to this. So let's look at the predicates of the second one. So basically this one. So attack results in facing, be armed with, compromise, execute, die, discuss with, um, retreat from, be damage. Um, so you can see some of these results are actually very noisy. Sometimes in order to get better results, we can aggregate some of these columns. Like for example, here we can just aggregate this, and by aggregating this, because of our restricted number of pre-computed schemas, we also aggregate over this. So these two columns they disappear, and what remains is this, and this, and this. Uh, so okay, so attack results in distract, flee, attack, be kill, die, stumble into, attack, surrender, withdraw, suffer, succeed, come under, attack, massacre. And let's try also aggregating over this. Kill, attack, lose, leave, come under, die, order, flee, defeat, suffer, fire, win, be shoot, be kill, occupy, be die, fall, surrender. Look at the second column, profile view. As I mentioned before, profile is is basically the combination of all statistics from all of the existing um, schemas. So in order to query from profile view, things are simpler. You can just enter the pivot node that we have for each of these schemas, and you will see the results. For example, let's try attack. And descends, which was the other one. And so basically, as you can see, these are all possible schemas that you can query with the graphs in the previous page. And all of these contain attack as their as one of their nodes. So noun phrase after attack. I think we actually went through this example. And yeah, so you can go through these tables and see whichever you want, whichever you like. You can try to use them in your work. You can try to refine them before using them. You can get intuition about the data, and that can help. You can also query from named entities. I can query uh, hold on. Yeah, this is the profile for Obama. So basically, all of these statistics uniquely, or not essentially, not really uniquely, but these are the statistics which correspond to the profile of Obama. Yeah, you can think of this as like a representation for Obama as an entity which is uniquely defined as it is disambiguous. Okay, so let us know what you think about our demo and give us feedback. Thank you.